All right, welcome everyone. We've kind of we're getting close to the end here of Chem 151. The topic for the lectures we want to start today is Chapter 9. It is the last chapter we're going to cover. Maybe that's a encouraging thing for you. Maybe you are hoping this could go on even longer. But the topic of Chapter 9 is molecular geometry. So we want to start to think about the molecules we've been drawing, particularly in Chapter 8, we learned how to draw a Lewis structure. How do these structures relate to what is the actual shape and some of the properties of the molecules that we're looking at? So you probably noticed there's no lecture note outline for Chapter 9. That is on purpose. I think a lot of the material in Chapter 9 is really just applying ideas that you already have in your head. Ideas like what are the angle between two bonds? What shape do objects make if we kind of imagine how the electrons interact? So the point that I want to make with the discussion of Chapter 9 is you can reason your way through all of the questions that we are asking in Chapter 9. You don't need a table. You don't need to be looking up every time what a shape is, because if you draw your Lewis structure correctly, you should be able to just figure it out from the principles. So as a consequence of that, we're going to start with basically a close to blank piece of paper, and we're going to build a table, and we're going to imagine all the different possible shapes that could occur in the Lewis structures and molecules that we draw. Then we'll talk about how we can decide if those molecules are polar or not. That again is going to be relating ideas about these shapes. And in the last part, we'll cover a little bit the formation of a molecular orbital. So this is a kind of a combination of the atomic orbitals we talked about back in Chapter 7. There's another way to kind of imagine how bonding occurs that involves overlapping those atomic orbitals to make molecular orbitals. So I just want to kind of introduce that idea. But then again, it's going to be very visual. We know that an s orbital is a sphere. What happens when we kind of merge two spheres together and imagine those waves interacting in different ways? So it's again something that I don't think we want a picture and me pointing it out on a picture. I think we want to think about what it looks like and then draw it ourselves. And that's the best way to kind of understand what's going on there, I think. Now, there is one idea that I do want to discuss before we kind of jump into evaluating molecular shapes, and that is often referred to as VSEPR. So it's an acronym here, VSEPR. This stands for valence shell electron pair repulsion. And this is a theory. This is a theory that attempts to describe the shapes of molecules based on the idea that electrons are going to repel other electrons. So all of that's in there. We have the valence shell electrons, which are the electrons we used to draw the Lewis structure to imagine the bonding, and the non-bonding electrons around every atom, and they're going to repel each other. Now, pair is a little problematic here because even though electrons are generally in pairs, there are certainly cases where electrons are not in pairs, where an electron is by itself, or where an electron exists in something like a double bond, where there's more than a pair of electrons, where there are maybe 4 or 6 electrons if it happens to be a triple bond. So let me show you here. This is the table we're going to make, and I put it on a separate piece of paper because I don't know that we'll fit all of this on one piece of paper. So I may have to kind of move the heading to a new piece of paper at some point, and out of laziness, I didn't want to have to rewrite it. So I put it by itself on a piece of paper. I'm going to start the table on this other piece of paper. But maybe you want to pause the video so you can copy all these down. The first thing we're going to think about, and this would stem from the Lewis structure that we just drew, is we want to look at how many sets of electrons are around the central atom in the Lewis structure. And there's a reason why I've switched to sets here instead of pair. So you hear the acronym VSEPR, it's got pair in it, but it's a little more complicated than pairs. So when I say set, I'm referring to things like double bonds. A double bond is a set of electrons because it's more than a pair. It's 2 pairs of electrons, but they're located in exactly the same place around the atom where the double bond occurs. So a double bond counts as 1 set. A triple bond counts as 1 set. a pair of non-bonding electrons counts as one set. But if we do have that kind of unusual molecule where there's an unpaired electron located around the central atom, that would also count as a set. So pair's a little too simplistic, right? We want to count the sets of electrons. Okay. After we figure out how many sets of electrons there are, I'm going to do what I call a point drawing, which will just give us an idea of where those sets of electrons will distribute themselves. Again, it's based on the idea electrons want to get as far away as they can from any other electrons that are around. This will lead to us describing an electron geometry, so a geometrical description of the molecule based on where the electrons are around the molecule. That will allow us to give an approximate estimate for what the bond angles are. What is the angle between the bonds in the molecule? And that can be helpful information to think about reactivity and things like that. Combining the electron geometry with some of the characteristics of the sets of electrons, that'll maybe become more clear when we see some examples, we will define a second geometry called the molecular geometry. Now, in common parlance, this will often be referred to as the shape of the molecule. In some cases, the electron geometry, the molecular geometry will be the same, and the shape will be the same as well. But we'll see there are other cases where these will differ, where the molecular geometry will kind of be a subset of the electron geometry. So we want to be able to describe both of them. But in particular, the bonds come from identifying the electron geometry, and then the shape is what we use to describe the characteristics of a particular molecule. And then lastly, I'm going to give you an example. So a molecular formula of a compound that would fall into the category we've just described. This would be a really good opportunity to get a little extra practice with Lewis structures if you're looking for that, because I'm going to give you the formula. Like maybe occasionally I'll draw the finished product, but this would be a good opportunity to kind of test. If I start with that formula, will I end up getting the same structure that was described and figuring out that it falls under that category? Okay. Now let's start off. Try to make sure I keep this in the right position for where I have my camera set up. We start off with the simplest molecule. So I'm just going to start off with what I would call sort of a trivial molecule, which would be one that doesn't even have a central atom. Right? So we're counting the number of sets of electrons around the central atom. What if there is no central atom? Right, so the only molecule that would have no central atom would be a diatomic molecule. So a diatomic molecule pretty much looks like that. There's just those two atoms involved, right? Because there's no central atom, we can't really worry about how these sets of electrons are distributed about a central atom. So there is no electron geometry in a diatomic molecule, and there is no bond angle. You need three atoms to have an angle. There has to be a central atom, and it has to have two bonds going away from it to have an angle. But we would describe the geometry of this molecule. This is a linear molecule. You only have 2 points that you can connect them with a line. So we would describe this geometry as linear, right? And any of the diatomic elements we've talked about would fall under this example. Things like H2 or N2. It could have different types of bonding, but still just two atoms. And it doesn't have to be the same atom as long as it's diatomic. Something like carbon monoxide would fall under this category as well. Okay. Now, moving on to maybe molecules that really do have electron geometries to worry about. The simplest, the next in the order of moving to increasing complexity would be if there are two sets of electrons. So the next category would be two sets of electrons. Now again, we're referring to a central atom here. So if there are two sets of electrons around the central atom, we would have kind of an atom in the middle, like that. And then the two sets of electrons need to spread as far away from each other as they can, again, because electrons don't like to be close to other electrons. So the two sets here, the bonds around this central atom, are going to move to exact opposite sides so that those electrons get as far away from each other as possible. And if you're having any trouble visualizing that, imagine your two hands represent the atoms at the end of the bonds, right? How far apart can you get your hands? You can spread them, put your arms straight out at the shoulder. That's as far apart as your hands can get. Your arms are now in the shape that I drew, right? And that would be a linear shape. So this would be a linear electron geometry. The sets of electrons are arranged in the shape of a line, right? And the angle here between the bonds, we have two bonds coming out of the central atom now, so we do have an angle, is 180 degrees. Okay. Now, in this case, and we'll see this is always the case when all of the sets of electrons are bonding sets, the molecular geometry, the way we describe the shape of the molecule, is going to be the same as the electron geometry. This we would also describe as a linear molecule. It is shaped like a line. Okay. The examples here, and we've seen a couple in our practice, but probably the most common example here would be carbon dioxide. Right? You end up with carbon in the middle. You end up with two double bonds to the oxygens, right? And if we're looking at this molecule, right, this double bond would represent one set of electrons. This double bond would represent another set of electrons. That's two sets. This is a linear molecule. Okay. Another example that we saw here would be thiocyanide ion, and it had two resonance structures. So both of them are, let's see, the other one would have a single bond to the sulfur and a triple bond to the nitrogen. Both of those also have two sets of electrons around the central carbon atom. So it's either two double bonds or it's a single bond and a triple bond. But either way, that's two sets of electrons. And either way, that ion would be described as having a linear geometry. Okay, now don't get worried. Things are going to get more interesting. We'll get more complicated in the geometry as we go to higher numbers, but we'll cover that in the next video.